I want to point out here that this is not an ideal transformer problem. And the reason for that is we started with an infinitely long wire along the z-axis, carrying some finite current I, which means that the flux through that loop, which is this infinitely long wire along the z-axis, extended out to infinity at the top and along the bottom. So this is at r equals infinity, and these are at z equals minus infinity, and this is at z equals infinity. This flux is going to be the integral from minus infinity to infinity in z, 0 to infinity in r, of b dot ds. And this b does not equal 0. So we end up with like infinite flux. Now I told you that an ideal transformer has equal flux in both loops. And the flux that we found for loop number 2 is definitely finite. So phi1, flux number 1 here, does not equal flux number 2 by any means, which means that it is not an ideal transformer. And we can't really talk about the different ratios of the numbers of loops or anything like that. However, it does have some interesting and important aspects of transformer problems, including this question of how much flux and what is the transformer EMF. So that's why we're doing this problem, even though it's not an ideal transformer. And we can find VEMF. So previously we found that VEMF is equal to minus the time derivative of mu I c over 2 pi. Remember, c was the z dimension of that toroidal ferrite core that they had, and times the natural log of b over a, and b over a, where b was the outer radius and a was the inner radius. If we put ourselves in phasor domain and we have some values for all of these numbers, then we can actually work this out. So a is going to be 5 centimeters, b is 6 centimeters, c is 2 centimeters, mu is 4,000 times the permeability of free space, the frequency is 60 hertz, and the amplitude of the current is 50 amps. Now this has to be, those 50 amps are at this frequency of 60 hertz. So if I were to write down what that current is, I is 50, we can choose sine or cosine, so I'm just going to choose cosine here, cosine of 2 pi times 60 hertz times t. But I'd rather do this in phasor domain. So since I chose a cosine for the current, I can say that the phasor version of this current is just 50. Because it's got 0 phase, it's just 50. When I substitute all of this stuff in, and I evaluate this time derivative, let's evaluate the time derivative first. The only thing that depends on time is the current. And when you take the time derivative of a phasor, you get a factor of j omega. So my new expression for the phasor version of VEMF is, let's go back up here. In fact, I think I can zoom out. Oh yeah. J omega mu c, phasor version of I, divided by 2 pi, ln of b over a. I can make this a little bit simpler by noting that omega is just 2 pi times the frequency, so then it becomes j f mu c, phasor version of I, ln of b over a. I'm going to take all of that stuff and multiply it out in my favorite calculator, which is just the search box on Google, and figure out what the answer is. So let's see, we had 60 hertz times 4,000 times, oops, that's not G, times the magnetic constant times 50 amps times 2 centimeters times the log, whoops, I gotta do multiplied, times the log of 6/5. And our result is 0.024 volts. So going on back to my notes page, I can write down that my final answer is 0.024 volts. Oh, wait, it's not, because I have that factor of J on the front that I didn't include in my Google. So it is, and I need this minus sign that I also neglected to propagate through. So that minus sign needs to be here in front of the J omega, and it needs to be there. So my answer is minus J 0.024 volts. That's my final answer.